Hello everyone and welcome to another video. Today I'd like to continue our discussion on ordinary differential equations. Now, if you've been following along with the series so far, you've seen we've already discussed how to solve differential equations, namely linear ordinary differential equations, using the Laplace technique. And we saw that that was a very effective way to go about doing this. Today what I want to do is I kind of want to step back. Traditionally in a lot of math curriculum and courses, they'll present what is called the, or sometimes referred to as a quote-unquote traditional way of solving ordinary differential equations before talking about the Laplace method. And we talked about this in a little bit backwards order. So what I want to do today is go back and take a look at the, I guess, normal way of solving homogeneous linear ordinary differential equations. Now again, today I want to focus on the homogeneous adjective. In the immediately preceding lecture, we'll tack on a non prefix to this and look at the non-homogeneous solution. But today I just want to take a little bit of a step back and look at a sort of mathematical approach of solving homogeneous linear ordinary differential equations. So again, just to refresh your memory, I think the easiest way to go about this is to look at a concrete example. So remember, what we're talking about when we say a linear ordinary differential equations is we are looking for a solution, something that might look something like, I don't know, how about x double dot of t plus x dot of t plus x of t, right? Some combination of the signal or the function we're looking for, which is x of t, right? So it is a function of the independent variable t, which in a lot of cases is time. So think about x as being like the position of a vehicle or a block or something like that, or it could be the altitude of an aircraft or whatever the signal needs to be. But this signal needs to add up and somehow be related to its derivative, right? The first derivative of the signal with respect to the independent variable, and then the second derivative of the independent of the dependent variable with respect to the independent variable. And you know what? The linear portion means that you can take combinations of these and maybe even stack on coefficients, like how about a, b, c, right? And now we have a linear ordinary differential. Well, I guess we need to put the equation part, right? I need to have an equal sign in here to make this an equation. And what this homogeneous portion or homogeneous adjective means in this descriptor means that this thing is equal to 0. Okay, so what this is, sometimes you may hear this referred to as, for the control systems people, is like a linear time invariant system or an LTI system. Sometimes you might hear this again, well, this might be a LTI system. LTI typically implies that sometimes you might have an input on this side, so where it would be non-zero, and that's what we're going to talk about next week when we get into the non-homogeneous portion. But for now, homogeneous means it's equal to 0. So there's no external excitation, no external inputs to this system. Okay, now this is the differential equation part, and a lot of times we are going to see that actually there are a family of functions that are going to solve this equation, right? There is not a unique solution to this differential equation. To narrow down the solution space, what we'll typically see is there are some also initial conditions that are, or boundary conditions that are attached to this problem. So meaning you need to find an x which satisfies this in the sense that I take its second derivative, I multiply by a, I take its first derivative, I multiply by b, I take the signal itself, multiply by c, add them all together, it equals 0. And to add on the requirements on top of this, what you will also see is a set of boundary conditions. So I'm going to say you have to solve this thing with the conditions that the signal at some specified time, let's call it t0, this has to equal some value. Let's call that value, how about x0, okay? And furthermore, since this is a second order differential equation, we actually need two initial conditions to fully specify the problem. So also let's specify the boundary condition is x dot at some other, let's use the same time, at time t0, that has to equal some other number like x dot 0. Let's call it this, okay? So you're saying this is the equation of motion if you want to think about it here. The signal has to obey and solve this combination, but also the position of the signal or the position of the block. Again, we're thinking that x, I always think it's helpful to think about x as being like the position of a mass spring damper or something like that as it's moving around. So the position at a specified time has to equal a specified value. So it needs to be 3 meters to the right. And similarly, the velocity of that at that time t has to equal some other value. So it needs to have a velocity of, I don't know, negative 2.5 meters per second, meaning it's going to the left, or however you set up the problem, right? So this is the full problem. So this, let's box this up maybe and say this is sort of your homogeneous, well actually here, I don't want to write this whole thing again in the interest of saving you time. It's this thing, right? This is our homogeneous linear ordinary differential equation. I guess you could say of second order or a second order, right? That's the additional adjective, because here we're only looking at a situation where the highest derivative of the dependent variable with respect to the independent variable is 2, as you can see right here, okay? Okay, so you might be sitting here scratching your head and thinking, all right, I need some kind of signal. In order to solve this, I need to propose a solution for what possible x of t's are going to have the feature that when I take its derivative, then take its second derivative, add these things all together, you might have some chance of it equaling 0, right? So for example, you could propose a few solutions. You know, you could propose, I don't know, pick something, right? X of t is equal to, I don't know, t squared. You could try this, right? You could try to jam this in here and you take its second derivative, multiply by a, take its derivative, multiply by c, take its derivative, multiply by, b and then c. Try to do this and get it equal to 0. You're not going to have very good luck with this. In fact, I can pretty much guarantee you're never going to be able to make it work with t squared. However, what you could do is, you know, if you think about this long enough, we're looking for a function that when you take its derivative, it doesn't really change too much, right? What kind of signals, when you take its derivative, does it not change a whole heck of a lot? How about an exponential, like an e to the t, and there might need to be some parameter r here. Let's call it, how about e to the rt? Okay? So you could propose, hey, this type of signal, or this function, would this have a chance of meeting this equation up here, okay? So in order to do that, let's go ahead and check this, okay? So let's go ahead and try to substitute x of t equals e to the rt into the, I'm going to call them the equation of motion, right? Or the ordinary differential equation, or the ODE. Maybe that's a better way to refer to this, right? But a lot of times people call these things, you'll hear these referred to, right? This is the ODE in question. But again, this happens in the context of dynamic systems a lot. So you might hear this called the equations of motion, or the EOMs, whatever you want to call them. But let's stick them into the EOMs slash the ODE, right? Stick it into there. So all I'm saying is basically you take a times, all right, I need the second derivative, so I need the d dt squared of, what's my proposed solution? It's this thing, right? It's e to the rt, right? Plus b times, what is this? The first derivative of the signal. So I need a d dt of the signal that I'm proposing. Again, this is e to the rt, right? Plus c times the signal itself times e to the rt. This better equals 0, okay? All right, so let's just start taking derivatives. And again, this is why the exponential function is great. You take its derivative twice with respect to t, right? What, 2 r's are going to drop down. So this thing becomes what? A r squared e to the rt. Would everyone agree that's this first term? Okay, plus b times this becomes r e to the rt, right? Plus c e to the rt has got to equal 0, okay? Well, look at this. All of these e to the rt's kind of are similar, so let's factor those guys out. So I end up with ar squared plus br plus c e to the rt has got to equal 0, okay? All right, so now this gets interesting. You look at this thing long enough. Let's examine this term here, e to the rt. You're going to note here that what? E to the rt, this is never equal to 0 for all values of r and t, right? There's no value of r and t you can jam in here to make this term equal to 0, okay? So if that's the case, the only way, well, I mean, heck, that you could divide both sides by e to the rt, what that means, right? Or the other way you can think about this is the only way to make the left-hand side equal to the right-hand side, or in other words, equal to 0, is this has to be 0, right? This must be 0. Okay, so the characteristic here is that this expression here, we must have AR squared plus BR plus C has got to equal 0. Okay, so again, this is almost like showing you the property of the R, or the property of the solution, or a characteristic of the solution. And in fact, that's what this is referred to. This is referred to as your characteristic equation of this second order linear ordinary differential equation, because you solve this thing and you will know now what type of a solution is going to solve this differential equation. So this here, again, is incredibly important. If this is the characteristic equation, which is going to tell us a lot about the actual solution of this ODE. So you stare at this thing long enough and you say, okay, that means I have to solve this thing. What am I allowed to, what's the parameter I'm solving for? So again, you come back over here to your ODE. These parameters A, B, and C, these are given to you, right? These are constants of the problem. Again, think about this. If this was describing a mass spring damper, right, or a block that was moving around, this A, B, and C, they have something to do with like the mass of the block and the spring constant and the air and the viscous damping coefficient. You don't get to screw around with A, B, or C, right? Those things are fixed. What you are free to choose here, right, when proposing this solution, the only parameter you're able to choose here is what does this value R have to be, okay? So you can think about this. This is effectively what? It's a quadratic polynomial in R, right? I need to find the values of R which make this equal, or if you think about this, again, stare at this, that means I'm actually looking for the roots of this this quadratic equation, right? Because I need it to equal 0. So how do you solve for the roots of a quadratic polynomial? Well, you're going to run over to your good old friend, the quadratic equation, right? Quadratic equation is going to tell you that there's going to be what? There's going to be two roots, an R1 and R2, right? And those are given by, well, any middle schooler will tell you, well, the quadratic equation is what? It's minus b plus or minus square root of b squared minus 4ac all over 2a, right? So here we go. You go ahead and you run over to whatever way you'd like to go and solve for this polynomial. I think the quadratic equation is probably the easiest way to go about this. And you'll basically get your solution of what values of R are permissible to make everything work out, to make the ordinary differential equation equal to 0, right? Okay, so if you are at all familiar with the solutions to a quadratic polynomial, you know that they kind of fall into 3 categories, right? So in this situation, you basically have a kind of a branching system where there's 3 possibilities. So your roots are, in one case, they could be real and distinct. Right, there could be no imaginary component. This discriminant here could be positive. If this thing is strictly positive, then you're going to have 2 R's, an R on the left and an R on the right. They'll basically be real and distinct. The other possibility is what happens if this discriminant was exactly 0? In that case, you're going to have 2 repeated roots. And in fact, they're going to also be real because there's not going to be any possibility for imaginary components. So the second possibility you could have here is you could have real repeated roots, right? You could have R1 at minus b over 2a, and R2 is also in minus b over 2a, okay? And finally, the third case you could have is if this discriminant here is negative, you try to take the square root of a negative number, this is going to become imaginary, right? So you could have complex conjugates roots, right? So there's these 3 scenarios that we may need to look at. So why don't we go ahead and let's consider this first case of the discriminant being positive. You basically have an A, B, and a C such that when you go ahead and solve this quadratic equation, you end up with 2 root locations, and those 2 root locations, they lie on the real line and they are different from one another, or they're distinct. All right, so let's take a look at case 1 where you have real distinct roots, meaning that you have an R1 which is different than R2, and both R1 and R2, they are real numbers, or they're real scalars, okay? So that's one way to think about it, okay? So in this case, let's go back to our solutions, and again, let's go ahead and ask and consider, here's one possible solution. is let's take a look at just using this R1 value, the first root that we get. Maybe it's like the minus b plus square root of minus b squared over 4ac all over 2a, right? So one solution, let's call it, how about x1 of t, right? This could be e to the r1t, right? And again, we know for a fact that this will satisfy the ordinary differential equation because, heck, we just did that, right? We by design picked R1 such that when we went through this whole rigmarole, right, this R1 was a root of the characteristic equation, so everything ran out. All the math worked out in the wash. I don't think I need to plug this in to convince you again. However, what's interesting is that constant multiples of this base solution are also a solution, meaning I can go ahead and tack on a constant. Let's call it maybe like a C1. Okay, so C1 is just an arbitrary constant. Now, this thing is actually also a solution, okay? So just to prove this to you, maybe what we should do is let's quickly do this, right? So again, we need to go and check that a times the second derivative of this thing, right? C1 e to the r1t, right? Plus b times ddt of C1 e to the r1t plus c times C1 times e to the r1t. Again, be a little bit careful. This c is different than C1, right? This c right here is the constant of the original ordinary differential equation. This C1 is this arbitrary constant we've introduced to our proposed solution, okay? We need to make sure this whole thing is equal to 0, okay? So in the interest of time, let me skip the nitty-gritty. I think everyone can go ahead and do all of these derivatives and make the calculations and the connections here and the algebraic manipulations, but you can eventually manipulate this sucker to look something like C1 e to the r1t times a r1 squared plus b r1 plus c is equal to 0, okay? You manipulate all this junk to be this left side, the right side is still 0. And again, you can see when you write it out like this, it's very clear that we chose R1 specifically. It's the magic value that is going to make this whole thing 0. So it doesn't matter what C1 value you choose here. It can be friggin' anything. This will always be true. So C1 is, it really is an arbitrary constant. You can go ahead and pick anything you want and it works, okay? Okay, so here's one possible solution. Interestingly, if you think about this, there's nothing special about using R1. Why didn't we go ahead and pick R2? It would have a lot of the same properties. So another solution is, let's do the exact same thing. How about let's say x2 of t is going to be e to the r2 of t, right? And by the exact same logic, let's go ahead and jam on another different constant, okay? So again, here, this C2 is, how about let's call it another arbitrary constant, right? And the thing here is that C2 does not necessarily have to equal C1. They can be very different. And again, you do the exact same logic, you'll come up to a very, very similar solution. Just change all these 1s to 2s, right? That's all we literally did here. But it's going to end up with the exact same feature that R2, right? I don't know why I just got that R2D2 flashed up in my head. But anyway, if you use R2 here, you will get the exact same solution in the sense that this is still a root to the characteristic equation, so it's still 0. So this thing is also a solution. So bada bing, bada boom, these two things check out, and we know for a fact that they are indeed solutions, okay? Now, here's the kicker. Let's say yet another solution is you take this and you add it to this, is you take x1 of t plus x2 of t, right? So this is now what? It's a C1 e to the r1t plus a C2 e to the r2t, right? You think, let's call this thing, how about x homogeneous of t, okay? Take this thing and we claim this is a solution, okay? Well, again, to check it, what you're going to want to do is you're going to want to go ahead and go a times d dt squared, right, of your x. I'm just going to call it xh, so I don't have to keep writing it, right? And again, xh is just this thing right here, right? This c1 e to the r1t plus c2 e to the r2t, that is xh, right? Maybe I should have drawn the arrow something like that, okay? So go run over to Mathematica or whatever your favorite symbolic manipulation tool is and go and plug this in, and then go ahead and do b times its first derivative of xh of t plus c times xh of t, right? And check to make sure that sucker is 0. So again, let me bore you with the, or let me spare you the boring details, and I'm going to skip that. And hold on a second, sorry.
From our tower.
Okay, sorry, I'm back. So you go ahead and you plug all of that in, and again, check the notes if you want the details, or tell you what, I'll just flash up a screenshot of my Mathematica output so you'll believe that I'm not just jerking your chain here. But you can get this thing to look like this left side, you manipulate this thing to look like c1 e to the r1t times ar1 squared plus br1 plus cr1, or no, sorry, plus c, right? This plus c2 e to the r2t ar2 squared plus b r2 plus c, this better equals 0. And again, you see, this is beautiful, because again, we see that r1 is exactly the magic value to make this equal to 0. So this entire term here is going to be knocked out. And similarly, r2 is another one of the roots of this quadratic, which will make this 0, which will knock out this entire term here. So indeed, we get a big fat 0 is equal to 0. And again, this checks out. This is what we kind of refer to as our homogeneous solution. So this is sort of like a fundamental solution to our ordinary differential equation. We are now going to go ahead and say that, all right, R1 and R2 are fixed by the differential equation, right? We know what R1 and R2 are going to be. The second somebody gives you the A, B, and C of the differential equation, you can go ahead and calculate the R1 and R2. You can calculate those roots. The rub, what's interesting now is, how do we pick C1 and C2? Well, we're going to see that you need to choose C1 and C2 so that we can meet those initial boundary conditions or initial conditions that we were talking about. So tell you what, give me a second to pause the camera, erase the board, and we'll be back in just a second to do that. All right, so here we go. We've got our homogeneous solution. We just now need to solve for what are C1 and C2 in order to satisfy the original initial conditions. And again, I keep referring to these as initial conditions, but really I guess you can almost think of them as boundary conditions, because what we said was that this signal x at a specific time t0, right, at a certain boundary has to equal a specific value, right, which this value was called x0, or however you want to think about it, okay? All right, so in order for this to be true, what is the left side? The left-hand side is the function evaluated at time t0. So let's take our solution here and evaluate it at time t0. So this is pretty easy. We end up with now c1 e to the r1 t0, right, plus c2 e to the r2 t0 had better equal x0, okay? So again, maybe it's worth it to stare at this and remind ourselves what's known and what's unknown, right? What are we trying to solve for? So the things that are known, right, is we know what R1 is, right? Let me do this maybe in another color. So let's, how about say red is known, right? So we know R1, right? This was the root of the characteristic equation. We know root R2, that was another root of the characteristic equation. We know what T0 is, right? Because the boundary condition is going to say the signal at this specific time, usually this time T0 is 0 seconds. It's the initial time of the simulation start, or the initial time start time, but it doesn't have to be. It can be 1, 10 seconds, 5.8, negative 4 seconds, whatever you want, right? But this is going to be known. So we know T0 here, Okay, and again, you know this x0 term, right? This is where the system starts, the initial value of the signal, right? So you know this. So the things that we don't know are C1 and C2. So here is one equation and two unknowns, C1 and C2, okay? All right, so we got to keep going in order to fully specify this. So you remember the other initial condition that we had was we also had that the velocity of the signal at some time has got to equal some other value, right? Here's our other initial condition, right? We call this x dot 0, okay? So this was our initial condition number 2 or boundary condition number 2, however you want to think about it. So again, let's look at the left side. So again, the left side here, this is the time rate of change of our solution, right? Evaluated at time is equal to t0, right? That's what this left-hand side says, and that has to equal this value that's given to us, x0. So again, let's go ahead and just get this left-hand side. So I have to take the derivative, the first derivative of the homogeneous solution up there, right? So we end up with, what is this? It's a C1 R1 e to the R1t plus C2 C2 R2 e to the R2t, right? And then I have to evaluate everywhere I see t, this has to be a t0, right? Okay, so great, that's the left-hand side. Again, this has to equal x dot 0, okay? And again, what do we know? We know R1, we know R2, we know t0, we know this initial velocity, we know this number. So again, we just don't, we know R1 and R2 here, right? So here's the other equation. So here is the equation number 2. So if you look at this equation and this equation, right? This is two equations, right, for two unknowns. And the unknowns here are C1 and C2. So basically just run, again, so you need to solve these two equations simultaneously for these two unknowns. So run over to Mathematica, do whatever you want. Again, here's a screenshot of when I did this in Mathematica and had it solve for C1 and C2 for me. And the solution we end up with here is that C1 has got to equal, it's a little bit odd here, so let me write this thing out, x dot naught minus R2 x0 all over R1 minus R2, right? Yeah, there we go, times e to the negative R1 t naught, or t0, and finally C2 is equal to x dot 0 minus R1 x naught 0 all over R2 minus R1 e to the minus R2 t0. Great, so there we have it. So again, the left-hand side, we know everything on the right-hand side, and then that'll give us C1 and C2, okay? So what we end up with here is we have basically fully specified and solved the linear homogeneous second-order ordinary differential equation. So just to summarize where we are right now, right? The ODE in question that we're looking at is ax double dot of t plus bx dot of t plus cx of t. It's got to equal 0. Here is our linear homogeneous second order ordinary differential equation. That's kind of a mouthful, right? And then we said this thing has boundary conditions or initial conditions of the signal at this time t0 had better equal this value x0, and the velocity of the signal or its first derivative of the signal at this time t0 had better equal this other value x dot 0, okay? If this is the problem, right, so here's the problem we're trying to solve, right? The solution to this problem is this is the function that solves it, right? And here we saw that the R1 and R2 were given by basically the roots of the characteristic equation or the roots of this second order quadratic polynomial. So this was minus b plus or minus square root of b squared minus 4ac all over 2a, right? And again, if this thing was real and distinct, keep in mind, right, the thing that the solution we're developing, this solution here is valid if R1 and R2 are real and distinct. And I guess technically this actually works for the complex conjugate case here. We're going to see that in just a second. But if they're real and distinct, here is the solution, right? And then the C1 and C2 are given by this expression right here. So here, all on one whiteboard page, we basically have the entire system set up and solved, right? So again, here's the problem, the fully specified, well-defined problem. Here's how you would find roots of the characteristic equation. Again, it doesn't matter if the roots are real or distinct. This will always work here. But if the roots here are real and distinct, here's the solution, right? It's just a combination of exponents. And then to get these C1 and C2, you basically just plug in boundary conditions and initial conditions to your problem, okay? So let's go through an example of this just to make sure we're all on the same page. All right, so let's look at a numerical example. So here's the differential equation I'd like to solve. So you can see in this case, A is 1, B is 5, C is 6, okay? And here's the initial condition. So the initial position is at 2, and the initial velocity is at positive 3, okay? All right, so let's go ahead and walk through this. So the first thing to do, let's look at step 1 here, is let's go ahead and find the roots of the characteristic equation, or the char EQ, right? The characteristic equation. Okay, so again, you can pretty much read it straight off the bat, right, from the ordinary differential equation. So the characteristic equation is r squared plus 5r plus 6 has got to equal 0, okay? So again, there's your quadratic polynomial. You run over to your good old friend, the quadratic equation. That's going to tell you r1 and r2 is going to be negative b, right? So it's minus 5 plus or minus square root of b squared. So it's 5 squared minus 4 times a times c all over 2 times a, right? A is 1 in this case. Okay, so you do this thing and you come out with roots here of r1 is going to be negative 2 and r2 is going to be negative 3. Whoops, sorry, that should be negative 3. Okay, so there's our two roots. So again, you look at this thing and you say, okay, what situation do we fall into? Well, you can clearly see that these are real roots, right? There's no imaginary component, and they're distinct, right? They are not repeated. INCT, right? There you go. Okay, so in that case, we pretty much know, per our discussion earlier, is that the solution, or the x homogeneous of t, right? The homogeneous solution is just given by C1 e to the r1, right, which was negative 2t, plus C2 times e to the r2, which was negative 3t, right? So here's the solution to this, okay? All right, so now let's go ahead and do step 3 here, which is basically apply the initial conditions to find C1 and C2, right? These two guys, okay? So, again, what we ended up with is, again, you could plug into that big expression we had earlier, but you know what might be almost more interesting is let's just apply the initial conditions and see what we end up with, right? So, x of 0 had better equal 2. Okay, so x at time 0 is basically this function at time 0. So this is c1 e to the negative 2 times 0, right? Plus c2 e to the negative 3 times 0 has better equal positive 2. Okay, so obviously this is what? This turns into a 1, and this exponent also turns into a 1. So we end up with c1 plus c2 has got to equal 2. Okay, so box this up and save them. Here's my one equation for two unknowns. Let's go ahead and apply the velocity initial condition, right? So this is x dot at time 0 has got to equal, what do we say, positive 3, okay? So again, I need to take the derivative of our solution, so that is going to give us what? It's going to give us negative 2c1 e to the negative 2t, right? Plus, or I guess this is now a minus 3c2 e to the minus 3t better equal 2, no, excuse me, 3, okay? And again, t should be at 0, right? So this t should actually be a 0, like that, okay? So great, what did we end up with? Same thing, so we end up with what? Minus 2c1 minus 3c2 has got to equal 3. Right? Great. So here's my second equation. So two equations, two unknowns. So solving those guys simultaneously. Solve simultaneously. Okay. We end up with C1 has got to equal 9 and C2 has got to equal negative 7. Okay. So great. So our total solution for this problem is 9e to the minus 2t plus, minus 7e to the minus 3t, right? Great, and again, this here is our solution. And again, just to make sure I'm not jerking or pulling your chain, let's run over to Mathematica real quick and double check that this solves the differential equation and obeys the initial conditions. And heck, maybe we'll plot it too for giggles. All right, so here we are in Mathematica. Let's go ahead and enter in our homogeneous solution for x of t. And this is what we want to check to make sure that it satisfies the differential equation. So let's do that first. So let's go ahead and just make ourselves a note and say, check that this solves the ODE. Remember, the original ODE said that we're looking for x double dot of t plus 5, whoops, so that should be a plus sign, plus 5x dot of t plus 6x of t has got to equal 0, right? So we got to check to make sure that's true. So let's go ahead and do this. So let's get the second derivative of this first. So here's the function, and I want to take its derivative with respect to t twice, and then I'm going to have to add that to 5 times the first derivative of the function. So x h of t with respect to t once, so there's our x dot term, and then finally plus 6xh of t, okay? And this whole thing at the end of the day better equal 0. So I'll say double equals 0, shift enter that thing. Well, that didn't really look quite right, so let's tell it to simplify this and combine terms, and there you go. So now this thing is true, so we see it does satisfy the ODE. So now the next thing we want to do is let's check that this satisfies the initial conditions, right? We saw that we need x at time 0 to equal, I can't remember exact the number, I think it was 2, right? And we needed x dot at time 0 to equal 3, right? So let's check that. So again, xh at time 0, this is pretty easy to do, right? This better equal 2. So let's go ahead and try that, and yes, it's true. Now, to get the second initial condition check, we need to go ahead and take the derivative of the function with respect to t, and then evaluate at time 0. So let's do that. So I'm going to take the derivative of the function, whoops, fat fingers there. Okay, there we go, with respect to t. So this is the derivative of the function, like this. I'll shift enter this. And now what I want to do is, again, I want to evaluate everywhere I see a t, I want to plug in 0. So I could define a second function here as this for the derivative function, but I'm kind of lazy. I'm just going to do this. I'm going to go say slash dot t goes to 0. So all this is doing, right, is our standard replace operator, where everywhere you see t in the expression to the left, it's just going to replace it with 0, okay? So this, we said, is effectively the initial velocity of the function. So this thing, we said better equal 3 if it's going to match our initial condition. So let's go and check that, shift enter, and, oh, whoops, okay, sorry. I need to put some parentheses on this to get this to work. Okay, so let's do that. There we go. Okay, so it's true. So it does. It satisfies both the original differential equation and the initial condition. So tell you what, let's plot this now to see what it looks like. Right? So I'll have Mathematica plot this function. That's pretty darn easy. Let's just call plot on xh of t, and let's plot this thing from time t equals 0 to, I don't know, how about 3 seconds or something like that, okay? And if we shift enter that, here's what the function looks like, right? You got t on the x-axis. Maybe to make this explicit, let's go ahead and add some axes labels to this thing. We'll say t is on the x-axis, and then homogeneous of t is on the y-axis. So there we go. So here's what the function looks like, and as you can see, it is the combination of exponents as we expect. It satisfies the initial condition in the sense that the initial position at time 0 is at 2, and you can see that the initial slope here at time 0 is positive 3. So, again, this looks great. Looks like it's working. All right, so before we leave this example, though, I do want to compare and contrast the approach we just took, which was the quote-unquote traditional way of solving homogeneous linear ordinary differential equations, and I want to compare and contrast that with the Laplace technique, which is what we talked about previously. So again, if you haven't watched our videos on the Laplace transform, the partial fraction decomposition, and the inverse Laplace transform, you might want to stop and watch those first. Or again, this is just a little bit of a side tangent just so you can see multiple ways of skinning the same cat. So I guess if you want to tune out for the next couple of minutes, feel free. But I just wanted to show another way that we could go about solving the same differential equation and hopefully start putting the inkling in the back of your mind that I actually think the Laplace technique is superior for a couple of reasons. And we'll see some of that here in the homogeneous case, and we'll definitely see that in the next lecture when we start looking at solving non-homogeneous linear differential equations. You'll see that the Laplace technique is far superior. So just keep that in the back of your mind as we walk through this example here. So again, what we want to do is we want to use the Laplace technique to solve this linear ordinary differential equation, right? So we said, okay, what we're going to do is we're just going to take the Laplace transform of both sides. So I'm going to Laplace transform the entire ordinary differential equation, right? X dot of t plus 5x dot of t plus 6x of t, right? I'm going to transform this from the Laplace from the time domain to the Laplace domain, right? So I'm going to Laplace transform both sides, right? Okay, so again, we can distribute this Laplace transform operator, since it's a linear operator, to each one of these terms individually. So this is the same thing as saying Laplace transform of x double dot of t, right? Plus, I guess, 5 times Laplace transform of x dot of t plus 6 times the Laplace transform of x of t is just equal to, I guess, Laplace transform of 0 is just a big fat 0 again here, right? Okay, so what do we end up with? So again, we're going to use the differentiation theorem. We see 2 derivatives in the time domain equal 1 over s squared in the Laplace domain, right? So this comes out to be 1 over s squared times x of s, right? But then again, remember that we need to take into account the initial conditions, right? So this is s squared, or sorry, excuse me, I got too excited here. The s squared, right? The integrals are 1 over s. 2 time derivatives or dots are s's, right? So 2 time derivatives is an s squared, okay? So anyway, s squared times x s of s minus s times x0. So again, this is the initial condition in the time domain, right? Minus x dot of 0. Right? So that's this first term. So this term here becomes these 3 terms. Okay, so maybe let's put this in parentheses just to keep them all the same. Okay, plus 5 times, okay, this term, Laplace transform of a single time derivative. So again, that's just a single s in the Laplace domain times x of s, right, minus x0. So again, the initial condition or the initial position shows up in this term. Okay, plus 6 times, I guess this just turns into x of s, right, is equal to 0. Okay, so again, we have pretty much all the information we need, because what is x of 0? That's right here. It's just the number 2, right? What is x dot at time 0? Well, it's right here. It's just the number 3. So this whole thing becomes s squared x of s, right, minus what do we say that one was? That's 2s, right, minus 3, right? This thing plus 5 times s x of s minus, should be minus 10, right? I think because I distribute, well, no, sorry, I left the 5 outside. So this is just a 2, like that, right? Plus 6x of s, right, is equal to 0. Okay, so now you go ahead and you collect terms and you solve for x of s, right? Because we solved. That's the whole power of the Laplace technique, right? The Laplace technique turned an ordinary differential equation into an algebraic expression, right? So if I solve for x of s, you can basically isolate it, right? And you end up with this thing is 13 minus 2s all over s squared plus 5s plus 6. Okay, and again, what's interesting is take a note that, look at this, the characteristic equation shows up in the denominator of this complex expression, right? So this characteristic equation is the same characteristic equation over here. So again, we see this duality of using either the traditional technique or the Laplace technique. It really kind of are the same expressions or the same approaches, right? So here, let's just make this a note. The Char equation shows up again. This is pretty neat, right? So again, if you remember our Laplace technique, in order to figure out what is the appropriate partial fraction expansion of this, we needed to solve this characteristic equation to figure out in the case, are we in the real distinct roots? Are we in the repeated roots? Are we in the complex conjugate roots case? Well, we already solved this. We know that this is in the distinct real roots, right? So we know we fall into this case 1, right, of distinct real roots. Therefore, that suggests a very specific type of partial fraction expansion, right? We're going to try to take this expression of 13 minus 2s all over s squared plus 5s plus 6, and we're going to try to turn it into an like an a1 over the s plus the first root, right? We said the first root was at s equals minus 2, right? Plus an a2 over s plus 3, right? The second root was at s of minus 3, right? Okay, so you go ahead and this is the partial fraction expansion that you want to do. Again, we hammered home how to do partial fraction expansion in our partial fraction expansion and decomposition video, so I don't want to belabor the fact and repeat that all here. I'm just going to say ... I'm going to assume you've watched that video and you know how to do this partial fraction expansion and find the constants, a1 and a2 to make the left-hand side equal to the right-hand side. And what you're going to end up with here is this thing is going to look like 9 over s plus 2 minus 7 over s plus 3. Right? Okay, so this is what x of s, an alternative expression for x of s is. And now this is beautiful because this looks very easily inverse Laplace transformable, right? So now if I want to find x in the time domain, it's just the inverse Laplace transform of the signal in the Laplace domain. So again, watch our inverse Laplace transform video on how to do this, but I basically just have to inverse Laplace transform this first term, and actually again, I'm going to pull the 9 out, right? So this is 9 times the inverse Laplace transform of 1 over s plus 2 minus 7 times the inverse Laplace transform of 1 over s plus 3. And again, this is directly inverse Laplace transformable, so is this. So we end up with x of t is equal to 9e to the minus 2t, right? Minus 7e to the minus 3t, right? Which was the exact same result we got using the traditional approach. So again, there's more than one way to ride this donkey, right? You either do it the traditional route or you use the Laplace technique. We both end up with the exact same homogeneous solution to this ordinary differential equation. All right, so let's move on to now case 2. What if you had repeated real roots? So let's just modify our differential equation ever so slightly. So how about make it look something like this instead? And let's use the exact same initial conditions that we had in the previous problem. Okay, all right, something like this. Okay, and now let's see how this changes, okay? So again, let's go ahead and find the roots of the characteristic equation, right? So again, that's just solving r squared plus 4r plus 4 is equal to 0, right? You go ahead and run over to the quadratic equation. You're going to see that the discriminant is exactly equal to 0, and you're going to end up with an r1, which is the same thing as r2, and these are here at negative 2. Okay, so you've got 2 repeated roots at negative 2, okay? So, all right, what could you possibly do? You might be tempted to do something, let's call this like how about incorrect? I just want to show what might happen and what could go wrong, because you very well might likely say, all right, why don't I try the exact same thing we did last time in the real distinct roots case, and I'm going to say a proposed solution to this differential equation is something like a c1 e to the minus 2t plus a c2 e to the minus 2t, right? I'm just going to stick r1 and r2 right there, okay? So, okay, you can definitely try to do that, and actually what's interesting is you'll see that this actually satisfies the ODE. You know, you plug this in to here, and you will get a 0. Thumbs up. That seems great, okay? The problem here is you're going to have an issue if you try to find the C1 and C2, right? So for example, let's just quickly do this. So if I try to apply the initial conditions for position, right? Let's try to apply this first one where I said that x at time 0 has got to equal 2, okay? So this is just going to, the left-hand side is going to be what? It's C1 e to the negative 2 times 0 plus C2 e to the negative 2 times 0. It's got to equal 2. Okay, so you're going to have an equation of C1 plus C2 is equal to 2, okay? So you box that up and save that, okay? And then you go ahead and you do the same thing where you're going to try to say, all right, I need the initial velocity of this thing to equal 3, all right? That was my second initial condition. So again, you take the derivative of the proposed solution, you end up with what? Negative 2C1 e to the negative 2 times 0, right? Minus 2C2 e to the negative 2 times 0. It's got to equal 3. So you end up with, what is this thing? You end up with, it's a 1, so you end up with negative 2C1 minus 2C2 has got to equal 3. Or I guess you could rewrite this thing as I'll factor out the negative 2, move it to the other side. So I end up with C1 plus C2 has got to equal negative 3 halves. Box this up and save this. And then, look at this. Inconsistent. There is no way you're going to make C1 plus C2 equal 2 and simultaneously make their sum equal negative 3 halves. So problem right here. You can't do it, okay? So the reason this happened here is that this is actually the incorrect form of the solution for the case when we have repeated real roots. So the reason this is incorrect is because this is not going to work for us, okay? So instead what we need to do is you actually need to use a slightly different form of the slightly different form for homogeneous solution. So xh of t, right? For this case where you have repeated real roots, it's going to be a c1 e to the r1t, right? Plus c2 times a t e to the r2t. Right, and again, remember, R1 and R2 are the exact same case, okay? So again, the only difference, and something that is often missed here, is this second exponential has a linear t term in it, okay? Okay? So this is our proposed solution. So again, what you're going to want to do here is make sure that, again, check that this satisfies the original ODE, right? So take this thing and plug it into this and verify that you get a 0. And again, that is what you're going to end up with. And tell you what, here's just the screenshot of Mathematica to show that it does actually solve the differential equation. So I won't go into it, but again, take the screenshot's word for it or go plug it into Mathematica yourself. So this thing works. Check. Okay, so now let's go ahead and apply ICs. So it's basically, I mean, you've seen it multiple times now, so I'm going to go a little bit quickly, but I just need to make sure that this is true. Okay, so x at time 0 is 2. So, all right, so what does this look like? This is c1 e to the negative 2 times 0 plus c2 times, here's where the t comes into play. So this t becomes a 0 times e to the negative 2 times 0. This has got to equal 2. So this whole thing, by the time you evaluate and knock out all these zeros, you end up with basically an expression of what? C1 is equal to 2. Bam, got one of the constants, okay? Now let's apply the second initial condition, which is x dot at time 0 has got to equal 3. So again, I got to take the derivative of this expression with respect to time. So let's do this one slowly because this is where we introduce a slight interesting, it's not a wrinkle, but you can kind of see why this works out slightly better. So I'm going to take the derivative of the c1 e to the negative 2t plus c2t e to the negative 2t. I'm going to take its whole derivative and evaluate it at time equals 0, and I got to make sure that thing equals 3. So let's take the derivative of this thing with respect to t first. So this first term is easy, right? This is negative 2c1 e to the minus 2t, right? Plus, I got to take the derivative of this thing. Now, here's where it's interesting. You got to apply your good old product rule here, because, right, you got a t here, and then you have another function, which is a function of t. So this is actually what? This is, I guess, minus 2c2 e to the negative 2t, times t. I almost messed up my product rule here myself. So this is t e to the negative 2t, right? Plus c2, and then I take the derivative with this t is now going to go away, so this now becomes e to the negative 2t, right? Okay, that's this whole thing. That's the derivative, right? And then I got to evaluate this thing when t is equal to 0 and make sure this is equal to 3. So again, everywhere you see a t, jam in a 0. So this whole thing is going to come down to, negative 2c1 plus c2 has got to equal 3. So here's your second equation for two unknowns. So equation 1, equation 2, solve them simultaneously for c1 and c2. And what you end up with is, shoot, ran out of room. Let's come over here. Okay, so what you end up with at the end of the day is c1 has got to equal 2 and c2 has got to equal 7. Okay, so what we end up with is our solution to this problem of repeated roots is going to look something like a 2e to the minus 2t plus 7 times t e to the negative 2. Oh, sorry, negative 2. Did I get? Yeah, I think I made it. Sorry, small typo in here. Yep. There we go. Right? Okay, so again, feel free to plot this if you want to see what its behavior is. What's interesting, again, if you look at this, you might be tempted to say that this thing, it might explode, because you know that this term, this first term, this is a decaying exponential, right? E to the negative 2t, right? So this thing definitely goes to 0. And the question right here is, you've got a growing term, t, and you've got a decaying term, e to the negative 2t. Which one grows faster? Well, it turns out, right, that this expression here is of exponential order in the sense that you remember that all exponents are going to crush pretty much any polynomial. So any power of this is going to eventually be killed off by this exponential. This is going to decay faster than this grows. So this term will also go to 0. So if you plot this thing out, this thing also will still go, this entire expression will still go to 0, okay? Okay, so great. Yeah, I think you can go ahead and show that this thing satisfies the differential equation as well as satisfies these two initial conditions here, right? Okay, great. Let's move on to our third and final case. All right, so let's look at our last case, which is case 3, where you have complex conjugate roots. So again, we're going to look at the vex. Very darn similar example. I just changed this constant from a 4 to a 13. We're going to leave the exact same initial conditions, and let's run through the process. So again, first step, right, is we're going to go ahead and find our roots. And again, if you go ahead and solve for r squared plus 4r plus 13 is equal to 0, you're going to come up with two roots. So r1 is going to be here at negative 2 plus 3i, and r2 is going to be at negative 2 minus 3i. So we see in this case, we have a complex conjugate pair. And you know what? Let's put in parentheses. They are distinct in the sense that they are not repeated, right? These are two different locations in the real imaginary axis. So you know what's actually interesting? Tell you what, let's try to use the same technique we did when we had real distinct roots, right? We still have distinct roots. The only difference is they're no longer real. They're complex, okay? So you could go ahead and actually try and say, okay, xh, what I propose for this, well, it's just a c1 e to the r1t plus a c2 e to the r2t. Of course, r1 and r2 in this case are imaginary, but you know, you stick imaginary numbers in there. That's not a real issue. And then, so we would end up with, okay, this is now like a c1 e to the negative 2 plus 3i, this thing times t, right? Plus a c2 e to the negative 2 minus 3i times t. Right? You can go ahead and do that. It's a function. It appears complex. Again, I'm going to say it appears. I'm going to show in a second it's not really complex, but it sure looks that way. So now go ahead and, you know, la-di-da, go ahead and apply ICs, right? You apply your initial conditions to find C1 and C2. So again, do the exact same thing we did at the beginning of this discussion. So I will save you the gory details, but if you do that, you're going to come up with a C1 is going to be 1 minus 7 6i, and C2 is going to be 1 plus 7 6i. Okay, so what we end up with is our total function that we've got here, x homogeneous of t, is going to look something like 1 plus 7 6i times e to the negative 2 minus 3i. Oh, sorry. I'm flipping this. C1 is the negative. Let's do it like this. Sorry, in my Mathematica notes, sometimes it flips things around. Okay, so this is negative plus 3i, right? T. You got to make sure that the C1 matches up with the proper root. Okay. Okay, this thing plus 1 plus 7 6i e to the negative 2 minus 3i times t. Right? So, you know what? This thing definitely, it satisfies the ordinary differential equation. It satisfies the initial conditions. But the thing that should be going clang in your head here is it appears complex. Right? It appears complex / imaginary. So again, if this differential equation was describing the position of a block as it was swinging around or something like that, this solution kind of makes it sound like, wait a second, what the heck, is this Star Trek? Does the block become imaginary and warp its way to some weirdo location? So is this actually a valid solution? It turns out, actually, yes. You know what you can do with this, if you really want to, and I'll leave this maybe as an exercise to the viewer here, but you can basically at this point apply Euler's formula, right? If you remember in this previous video, right, where we discussed complex numbers and complex variables, we had a discussion on Euler's formula, right? Euler's formula basically said that you can rewrite a term that looks like e to the I theta as basically a cosine of theta plus sine theta I. Right? And again, if you want to get to that video, feel free to click on the card that's appearing up here in the upper right, or I'll do you one better. Tell you what, go to the description of this video, and I will leave a link to the exact video and timestamp where we discuss Euler's formula, so you don't have to dig around for it, to refresh your memory on what it does. But basically, what you can do is you can plug this in, and you can see these terms are in here, right? You can kind of see an e to the, here's kind of like your theta I here, right? Theta is 3t or something like that. You can jam this in here, do all of the reductions, and actually you can turn this thing into a completely real expression. And actually, that claim might be a little bit too much for you to buy right now. So tell you what, let's jump over to Mathematica and take a 30-second detour, and let me prove to you that this thing, even though there are eyes all over the place, if you were to work it out in Euler's formula and do some trigonometric simplifications, this thing turns into a real expression. So let's go do that real quick before we come back. All right, so here we are back at that same Mathematica notebook. So let's look at our example 3, which was our case of complex conjugate roots. Okay, and let me change that to a section. Okay, so in this case, maybe the first thing we should do is let's clear that variable xh that we had earlier, and then let's type in the new xh that we had for our complex conjugate solution. So again, here it is in the complex form. So I'll take off the semicolon just so you can see that, yeah, this thing's got eyes all over the place. And again, just for giggles, let's go ahead and verify that this satisfies the ODE and the initial conditions, right? So in our case, what was our initial the ODE? I think it was the second derivative of t, right, with respect to t twice, plus 4 times x dot of t right here, right, plus 13x x of t, right? And this thing was supposed to be 0, so again, shift enter that thing. Well, maybe it didn't look so great, so let's simplify this expression, have it combine terms, and yes, that definitely does equal 0. Let's go ahead and now look at the initial conditions. We needed xh at time 0. This had to be 2, and haha, look at that. That definitely works. And let's look at xh dot at time t equals 0, right? So that's that guy, shift enter that, and it's 3. So yay, look at this. This weirdo complex expression definitely satisfies the ODE and the ICs, but again, all these imaginary terms go clang in your head. So what we may want to do is, let's make another function. Let's call it xh, maybe real. So I would like to manipulate this expression. So Mathematica's got this great function exp2trig. So I pass this an expression with basically a lot of these Euler formula expressions in it, right? The e to the something I, and it should hopefully do some simplification. So let's do that. So I do this, shift enter that. It didn't quite get all of this. There's some hyperbolic cosines, but if I say full simplify this, full simplify, shift enter, look at that. This looks beautiful, right? This guy is a completely real expression, and in fact, again, it's the exact same thing, just in a different form, so I would completely expect it to satisfy the ordinary differential equation, right? So let's do that. So xh, now I want to look at xh real, right? And I want to make sure that this real formulation satisfies the ODE. Yep, it's a homogeneous linear ordinary differential equation that's equal to 0. And let's go ahead and get the initial conditions and make sure that those things work as well. So again, I want to look at now, what does this real function do at time 0? And what does its velocity do at time 0? And again, look at that. It definitely satisfies it. So this is a much better expression to use for the solution to our linear ordinary differential equation with complex conjugate roots.
Okay, so that was really interesting, right? We basically just showed that this thing, actually the other way you can write this, and which is probably a little bit more understandable, right, is this thing sure looks a lot like 1/3, well actually it doesn't look a lot like, it is the same thing as 1/3 e to the negative 2t times 6 cosine 3t plus 7 sine of 3t. Right? And actually, you know what? Let's move this 1/3 inside this expression. So again, the other way you could look at this thing, it's an e to the negative 2t times, I guess 6 over 3, what is it? That's 2, right? 2 cosine of 3t plus 7/3 sine of 3t. Right? So this is a much better expression, right? If we're describing a physical position of, if this differential equation represented the physical position of a block or something like that, this is a completely real expression, right? Which I guess, we show that, this looks imaginary, but it's not imaginary, right? You go through the work, you can get it to look like this, okay? So this actually yields some insight into this problem, right? If you look at this solution, right, what are some of these numbers that look familiar? Let me circle some of these. Like, for example, like this negative 2. Where did this come from? Well, if you come over and look at the root, right, you see that the root, this is like the real portion of the root, right? If we were to, again, plot on the real imaginary axis, right, where are these roots? So R1, this is like here at negative 2, 3, negative 3. So there's a root here. So here is R1 and here is R2, right? So there's this green part, right? So this distance here, right? Let's call this like sigma. That shows up right here in this exponent which precedes the oscillatory component of the signal, right? Now, the oscillatory component of the signal, if you look at it, right, what is the angular frequency at which these these sinusoids are oscillating? Well, it's right here, right? Here's this 3. I'm going to try to circle it in this kind of dying blue. Oh, sorry, this is on the way out, right? But where is that? That is like the imaginary component of the roots. So that's like this distance here, right? So let's call this distance like, oh man, this blue is really on the way out. Uh-oh. I don't know if this is going to work. I guess I'm going to have to do it in, well, okay, let me see if I can make the blue work. I just need to draw an omega. Ah, there, okay, that kind of worked, right? Okay, so you can think about these roots. You know, you could have rewritten this root here, R1 and R2. This is like a sigma plus or minus omega I, right? A real plus or minus an imaginary component, right? And the real component of the root shows up as the in the exponent, and the imaginary component of the root shows up in the angular frequency of the oscillatory component. So in other words, what I'm getting at is, you know what we could do? Let's try to propose a general form of the solution. Instead of using exponents, let's use exponents and sine and cosines, right? Let's use a function that looks similar to this, but maybe these constants, like this thing, let's call it a C1, let's call this a C2, right? So to make this explicitly obvious, let me go ahead and let's find ourselves some room. Where can we erase? Let's get rid of this junk, okay? This is what we were doing earlier. Okay, so let's go ahead and propose a different solution format which might be easier to deal with. So let's say x homogeneous of t. Let's pretend or propose a solution that looks something like e to the sigma t, right? That's the real part, e to the real part t, times, let's call it a c1 cosine of omega t plus C2 sine of omega t, right? That's basically the format that this solution took here. So again, we got to be very careful where here R1, 2 is given by sigma plus or minus omega I, right? So this is the general form of the solution, and we can show that you plug this thing into the differential equation, you know what? It's going to solve it for you. Now let's just do the exact same thing we did again or earlier, and namely, let's go ahead and apply ICs, or the initial conditions, to find C1 and C2. Right? So again, just for the sake of completeness, I guess I'll go through it one more time, but I think at this point everyone's got the hang of it because they've seen it twice already for the other cases. Where have I got this thing, right? So again, x0 has got to equal 2. Right? So what is x0? So x at time 0, this is e to the, what is sigma in our case? Sigma is -2, right? E to the -2 times 0. This whole thing times c1 cosine of, what was this? This is 3, right? This is 3 times 0, right? Plus c2 sine of 3 times 0. Right? Okay, that's this whole left term. This has got to equal 2. So again, you look at this thing. What is this goes to a 1. Cosine of 0. This goes to a 1. Sine of 0. This goes to a 0. So gosh, this comes out pretty darn easy. So C1 is equal to 2. Right? All right, here's one equation for, I guess, one unknown in this case. And then we're going to do the exact same thing. So x dot at time 0 has got to equal 3. And again, I think I'm running out of room, but I think everyone can go ahead and take the derivative of this thing with respect to t, then everywhere you see a t, jam in 0. That is going to give you a second equation for the C1 and C2. Solve these two equations with two unknowns, and you know what you'll end up with is, again, check the notes if you want to see the nitty-gritty details, but I think, you know, you all get the idea. What you're going to end up here with is C2 is going to equal 7/3, okay? Great, so basically done. Plug that into our expression and we end up with, as we would expect, x of t is going to be, what we get, e to the sigma. Sigma was -2. This is -2t times, whoops, c1 in this case. We just figured out what c1 was. It's 2 times cosine of 3t plus 7/3 sine of 3t. Great. Which again, I guess if you look right here, this is the exact same thing as what we saw earlier.
So again, if you were to go over to Mathematica and plot this thing and double check that it solves the differential equation and solves the initial conditions, you would definitely see that it does. And what this thing starts to look like, right, is you got x homogeneous of t versus t. It's going to start here at 2. It's going to have an initial slope here of 3, and it's going to be oscillatory here. So it's going to do something like that, right? I'll let you plot this for your own if you'd like to see it for your own edification. So, yeah, there we go. I think this is a good spot, actually, because if you think about it right now, we have covered all 3 scenarios, right? We covered the scenario of distinct real roots, repeated roots, and complex conjugate roots. So at this point, this is a pretty comprehensive way to solve linear, second-order, homogeneous ordinary differential equations, okay? And again, this is the traditional approach. You could, we showed a little bit earlier, use the Laplace technique if you're more comfortable, and that would fall through for all of these analysis. So what I'd like to do now is, on our next lecture, let's talk about what happens if the right-hand side is not equal to 0. What if we have a non-homogeneous linear ordinary differential equation? How can we go about solving that using traditional approaches like we've done here? Okay, and then we can compare and contrast it with the Laplace technique. So, with that being said, I think this is a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button, it really does help me continue to make these videos. And remember, the new videos should be coming out every Monday, so I hope to catch you at one of these future discussions, and we can all learn something new together. So, until that time, I think I'm going to sign off for now. Talk to you later. Bye.